Good evening, everyone. Sorry for the late joining. I was a little bit busy with another meeting. So just give me a minute to set up. Okay, so let's get started. So today we have more of a tutorial rather than practice questions about multiple linear regression or just multiple regression, we can call it. Okay, so let me walk you through how you go about it and the steps that you take while doing it. So let me first import the libraries. We have we need pandas, we need NumPy, we need Seaborn for plotting, and we need stat models for our this thing. These are the main things. We got the semester set for this. So if you remember, we worked with this California data set, so we can reuse that. So we can say For the California data set, we can this time actually use another pipeline. For the time being, we can say from sklearn.datasets import this thing. So we have fit California housing. Data is pd dot data frame. Okay, so we have our data set. Essentially, this is the California data set where we want to predict the median house value. So the values essentially goes from almost 0 to 5, where it is on a scale of 100,000. So when you say, let's say 3.5, multiply it by 10 to the 6 to get the actual value, 10 to the 5 actually, to get the actual price. So we have many different things. For example, what is your median income? How many rooms do you have? What is the population of the area? What is the latitude and longitude of your region? If we want, we can have some more details of our data before we start. For example, we could, because we have numerical data, we can do, for example, data to describe to see our stats. We can also check data.info to see whether there are any null values or not. There don't seem to be any null values in our data set, so that's also good. And if you remember, in the lectures, the professor said that you should plot essentially the what do you call it? Plot a scatter plot between the variable between the independent and the dependent variables. So, for example, in this case, uh, you have 9 columns, one of which is the target column, and the rest of them are independent. So you essentially have to create these 9 plots separately, and you also want to create a plot between each pair. That is this and this related? Is medical median income and average rooms related, and so on. So there is actually a shortcut method to do it rather than plotting each of them individually. You can use something called scatter image, scatter matrix, in fact, scatter matrix. So scatter matrix is a function from pandas. We can import this. So we can say from pandas.plotting import scatter image. If we call it on our data, and we can say give me a fixed size of 12 by 12. So give it a minute. Yeah, so you notice that this is a, how many are these? A 9 by 9 matrix where it automatically plots the scatter plot between all of your columns. Sometimes it's quite jumbled in this case because we're using all the data. If we rather sample, let us say some of our data points. So it becomes a little bit more clear. So for example, this is the median house value. We see that there is a linear trend between medium income and house. The house it doesn't seem to matter that much. There is a sharp rise with the average number of rooms. Similarly, with the average number of bedrooms, and we have other values as well. For example, in latitude, we see that there are essentially two separate groups. Similarly, in longitude, there are two separate groups of these linear trends. We can also measure the correlation between two variables. For example, we have average number of rooms in this row and we have average number of bedrooms in this row. So if you compare, this is average number of rooms and this is average number of bedrooms. So they essentially match up like this. So you can also compare two variables with each other. The only thing is you lose a bit of control over these scales because I mean, you see this is jutting up like straight up. If you were to plot it individually, you could maybe control this scale so that you would see more of a gradual slope rather than such a violent, slope. So that is one way to do it. So once we have this, we can also check whether there is any correlation between the columns or not. So why are we, by the way, checking for this correlation? If you would remember, we do not want two columns to supply the same information because it leads to multicollinearity. We'll see that in a few cells, but let's first say we want to see the correlation matrix. So we can just call data dot core. You would notice that we have medium income, house, this is just the correlation values. A positive value suggests that they rise equally. A negative value means that when one rises, the other falls. And if your value is close to zero, it essentially means that you have almost no correlation between the two. So this data, for example, this textual data, it is very useful, but because of its size, it is not easy to read for a human being. A better way to present it is using a heat map. A heat map essentially colors these individual values. A positive value should have let's say, a red color, let's say, and a negative value, we can assign it a blue color, and values close to zero, we can set them to, let's say, white or something. Okay, so how do you create a heat map out of a data correlation matrix? We can use Seaborn, this function. So Seaborn is another plotting library, just like Matplotlib. It is more aesthetic and has more capabilities compared to Matplotlib, but it builds on top of Matplotlib. So we can just call SNS dot heat map and we pass it the correlation matrix. If we just call it like this, so you notice that we have this heat map, and on the left side we have the column names just like that, and here we have a color. A brighter color essentially means that two things are correlated. A darker color means that they are not correlated. We you If you would like, you could pass annotation equal to true, and what that does is it fills the values inside these cells. But in our case, it would not look that great, so we can set it to false. And similarly, you can use a different CMAP. As I said, we could use, let's say, a darker red color for higher values, a bluer color for negative values, and a white color for zero values. So for that, you can say that, okay, give me a different color map. I would like a cool, warm color map, which would make it look something like this. If you notice, between our main predicted variable, that is the median house value, the medium income is the main predictor for this value. It has a very high correlation compared to this. Similarly, the house age and average number of rooms also have a positive influence on that. Other than that, they are mostly close to zero. The population, the occupation, the latitude, longitude doesn't seem to matter that much. Okay. And we also see, for example, the average number of rooms, this thing, and the average number of bedrooms have a high correlation. So this makes sense because if you have more rooms, you probably also have more bedrooms. A bedroom, because a bedroom is also a room. So this is a clear case of multicollinearity that can occur later on. So if we have this plot, we could draw, for example, the average number of bedrooms because of its correlation. We could, in fact, also drop one of lat. I mean, it doesn't make sense to me to drop latitude or longitude because they are not essentially correlated because like one gives you the x-axis, one gives you the y-axis. So I don't think we should drop that. So let's drop average bedrooms. You can see that our data frame now is the same, but I'd like to drop one of the columns. I would like to drop AVEP bedrooms, and then we can plot this again. Okay, so we have removed average bedroom. So this is our data frame now. So let us prepare the data for regression. So for regression, what do we need? We need the independent values in one set and we need the dependent value on the other set. So we can create our X, which would be our data dot drop this, and our Y value is exactly that. And we'd like to add an interceptor. Right, so what does that data look like? We have one interceptor, one. This is for uh, the constant value, the intercept for our linear regression, and for the rest of it, we have just dropped this one particular value, which is med-house value, because it is the independent variable. Our Y value is just the median house value. So with that, we can just train a model. We can say model is equal to stats model dot ordinary least square. I'll give it the dependent variable. We have the independent variables, and we can just call results is equal to model dot fit, and then we can print the summary. This would be better. Yeah. So we have our summary. We see that we have essentially a positive slope for the medium income, and the p-value is also close to zero. Almost all of them have a p-value close to zero. That is, they are significant, and some of them have a very small, let's say, slope, like 0.0097 for house age, which, as we saw even in the this plot, didn't matter that much. Like house age, it is pretty much scattered. It is not a good predictor of this. So you have all of these cases. Then you would notice that stats model is telling you the condition number is quite large. This thing. This might indicate that there is a strong multicollinearity or other numerical problems. So we did remove the multicollinearity earlier. For example, we removed the average bedroom, so this should not happen. The other thing that can cause this numerical problem, which it says is the instability, is that our columns have very different scales. For example, our population has a very different, I mean, scale compared to others. So notice that, let us say our house age, it has a minimum of 1 and it has a maximum of 52. Compared to that, our population is has a minimum of 3 and a maximum of 35,000. So these are very different scales. So when we have these very different scales, then the coefficients are also quite different for the two. And it makes the model sensitive for these very large values. Like if there is a small change in that, it can fluctuate drastically. So because of that, we are getting this, I mean, warning. I mean, it doesn't actually affect your model that much. I mean, your answers are still correct, but it is a bit unstable. So to combat that, we want to standardize our columns. That is to get all of these values into the same range. This has a trade-off because the moment you standardize, you lose a bit of interpretability because now everything is in the like same range and the coefficients are not in that sense. It's the same thing. So how do you standardize essentially? So you essentially what you have to do is you have to subtract the mean of each column and divide it by the standard deviation of that column. Divide by the standard dev of that column. You can have a library do it for you. So what we will use is from sklearn dot from sklearn pre-processing import standard scalar. Okay, so we have this. We can say our x scale is equal to, first create the scale. So we have our x values. Then we have model scaled is just our same thing. The x value has just changed. And we have results underscore scale equal to model underscore scale dot fit. And we can print. Okay, so we have something like this. Let me just check whether changed one as well. Oh, X scale is an array. If you give me, let's say the first two columns, just give me the first row. Yeah, so it messed up the intercept term as well. So maybe we should do it a different way. Rather than calling it on X, we should call it on this thing. Yeah, I think now it's better. Yeah. So now you would notice that our values have also gone into the negative because once you subtract the mean, you don't have to be in the positive sense. But everything is now in the same range, but it is less interpretable, but better for linear regression as a whole. You would notice that error that our model is now unstable has disappeared. So this is a thing that you can do, for example, to standardize your regression model. This is especially you do for other models that are more affected by the size of your essentially model, but linear regression is not affected that much. But just for stability, we can do that. So something to keep in mind. So now that we have these values, let us say, can we plot the residuals and check whether it holds? So the idea is if we would like to, the residuals should look randomly scattered around the zero line. That is the gap between our predicted value and the average. I mean, in our case, because it is the residual, it should not vary with x. If it varies with x, that means that there is actually not a linear relationship here. So the noise has some sort of relation with the x value. So to do that, we can first get our residuals. We can say residuals is equal to results dot res ID. So these results, I'm using the original ones rather than the standardized ones to, I mean, it doesn't matter, but just for to have values in the same scale. Then we can just plot it in a scatter plot. We can say, give me a scatter plot of the fitted values against the residuals. We can use a small marker with an alpha of 0.5. And if we say pld.show, marker, yeah, so we get something like this. So let us add a few more things and then we can comment on what we are seeing. So we can have a horizontal line at 0, and we can add a few things like these x value has my fetched value, the y value has the residuals, and then we can print show a xh line. Yeah. So you see that this blob essentially is random. But what is this straight line that we see here? This is definitely not random, right? This is not something that we would like to see. So this actually happens because the California housing data set, the median house value is actually capped at 5. If you know, you notice in like describe, it says median house value. The maximum value is a sharp 5. So what does that mean? If you plot the histogram for these values, for example, data dot medhouse dot histogram, you notice this, for example, we have a almost like a Gaussian thing, a bit tail, but I mean, we have this distribution. There is this weird thing at 5. That is, there is a huge jump at 5. So what has happened is every value greater than 5 has been clipped to 5 in the median house, this thing, right? And as a result, what happens is your model has essentially fit the data. I mean, fit the data for essentially this part, and these are mainly the outliers. You can consider that. So why is this particular thing producing residuals like this? So if you look at it mathematically, for all these points capped at 5, if you were to compute the residuals, how would they look like? We can say that our residual is equal to our observed value minus our predicted value, which is essentially our observed value is 5 for all of them because it is a constant minus our predicted value, whatever we predict. So you notice that this is like an mx plus c situation. So you have a constant term c, which is your insert, which is your intercept, and you have a slope of -1 times your predicted value. So this is a straight line, and this is exactly what you see. This line here is the residual line where the slope is -1, and you have this straight line. So that is why you're getting these values. We should, in effect, actually drop this particular value, which is capped at 5, because it is disturbing our model anyway. We does not provide any useful information in our case. So let us try to plot this particular thing without this. Okay. So we can first remove this data. That is this 5 column. We can say data uncapped is data median house value is less than 5. The rest of it is the same. We can say data uncapped dot drop drop the median house value, or y uncapped is data uncapped med house value. We add a constant, and then we can train our model. We can say our model uncapped is just our ordinary least square. My y value is the uncapped y value, and my x value is my uncapped x value. This would give me my results. We can call it results uncapped, which would be model uncapped dot fit, and then we can see the results. Mid house, there is a, yeah. So we get this. If we plot this thing again, this part again, see, now we have this blob and we don't have that straight line, and it is more or less a random distribution above and below the line. So we can say that our residuals have this property. Another thing that we can check is the QQ plot for our data. So how do you make that? You simply go for stats model dot QQ plot, and you can pass it your residuals, and it would look something like this. Okay, so in our case, we can also say that, hey, I would like a line at 45 degrees. Please use a smaller marker, and I would like some transparency. Okay, so we can get something like this for our QQ plot. So is there anything else that we would like to see? I think that should be pretty much it for multiple regression. So to recap, so what are we actually doing here? So initially we have our data to predict the medical house value. We have certain columns. We would like to see whether there is, I mean, the general description of our data. We see that we have very different scales for some of our values, like the population is in the thousands. This is in a scale of like almost 0 to 15. And the latitude, longitude also have quite different values. Like they even have negative values for latitude and longitude. We also check whether we have any null values that we should take care of in the beginning, and we see that we don't have any null values across the columns. Then we went for a shortcut function to plot the relationship between the every pair of columns. So this is a very handy sort of function, rather than plotting all of this by yourself to create this plot, design these subplots, and then have histograms and these scatter plots. You can just call a small function which can do it for you. Also, you don't have to do it for all these columns. You could pass, let's say, a subplot of the same. You can say, okay, don't give me all of these, give me a sample, but I'd like a smaller list. For example, we can only do it for med income and um, average rooms and let's say population, and finally our med house value, med house value. You see, you can also do it for a lesser number of columns to have like more information. We see that in medium income, between your median house value, there is a clear linear pattern. With average rooms too, there is a clear pattern of it's just a bit sharper. Similarly, with population, you could argue that there is something here. Okay, so going back to our original case where we had plotted more or less everything, give it some time. Yeah, so this is a plot. And again, because your data set can be very large, it's better to plot it over a sample than rather than the full data set. Okay, so once we have this plot, we would also like to see, are there any columns that are independent on each other? So the first thing is like our dependent variable has some correlation with the independent variable, which is good. That is what we want because that helps us predict the value. But we don't want two columns to have a correlation between each other. So is it a bad thing for two columns to have a correlation amongst each other? It does not necessarily affect your regression model, even if you keep that. The only thing is once, let us say two things have a correlation. Suppose both of them have a positive correlation with the predicted value. So what happens is your linear regression finds it difficult to give like responsibility for them. Like, should I give a positive responsibility to average rooms and just ignore bedrooms? Should I give half to this and half to this? Sometimes it can also happen that it can give more than required responsibility to average rooms. So like, for example, it can say I'll give a coefficient of 3 to average rooms, and to compensate I will give a coefficient of -1, let's say, to average bedrooms. So this would make it seem as if average bedrooms has a negative impact on your prediction and average rooms has a positive impact. But the thing is that because these two are correlated, they are just canceling part of each other out. So this makes interpretation difficult for your model. So that is why you don't want highly correlated columns in your data set. So we also saw that because we have this large, I mean, this is not large, it's fairly small number of features, but still we have too many numbers for us to digest as humans. We don't look at data like this. So rather than having these numbers, we are going for a heat map. In a heat map, you estimate, I mean, you sort of visualize the number based on its color. We can essentially, it's up to us which color map we use. By default, for example, if you pass it like this, it looks something, for example, like this. This has a like on the colder side, you can say it has darker values, and here it has lighter values. Rather than having this, because we have a split in the middle, we should have a white value at 0, and then we can use two separate colors. So it's up to you to use the cool color map. So because we had already dropped the average number of bedrooms, that's why it's not showing up. If we maybe restart the session and do a run log, we should get that. Give us a minute. Yeah. So in our heat plot, we say that we see, like, for example, in our final row, this is the predicted value, and the predicted value has a good correlation, a positive correlation with the medium income. It makes sense. It has a slight correlation with the house age and the average number of rooms, and for the rest of them, it does not depend that much on them. Okay. But we see, for example, in the rest of these values that there is a very strong correlation between the average number of rooms and the average number of bedrooms. You see this color, it's very close to 1. So we don't want that. So these two values are essentially collinear in this case. So we just drop the average number of bedrooms because average number of rooms essentially covers the same information. So once we drop that, we can again plot the same thing and it's okay. You could, in a sense, argue that, hey, why have you not removed latitude and longitude? We should remove one of them because there seems to be some negative correlation between them. In fact, almost equal to -1. That is when latitude increases, your longitude dips. But I would argue that these are essentially independent variables. It just happens to be like that because geographically, like what can you control with latitude and longitude? Right. In this case, maybe it could like the area is like such. For example, in this case, we saw that there are essentially two peaks in latitude. Similarly, there are two peaks in longitude. So maybe the data has is split in that direction, right? So you could make a case for dropping one of them too. So once we have this, we want to prepare our data for conducting linear regression. In linear regression, you essentially need two separate values. You want the independent variables in one set and you want the dependent variables in another set, your x and your y for your function. Now because you're training the linear regression, you also want a intercept term, and for the training the intercept term we have to prepend a column of ones. To do that we can just use the add constant function and we have our x value, and it is pretty straightforward to train the linear regression function on that, and we get our summary. In our summary we see that we have the slope of -40 and we have the slopes for our individual values. All of them are pretty much statistically significant, so that is good. We can essentially confirm that hey, there is some correlation, and as expected medium income has the biggest slope among all of them, which we also saw as a color here. Okay, that's good. And stats model gives us a warning. It says that your condition number is quite large, and this indicates that there is a strong collinearity, which we did remove, or other numerical problem. So, what could be the other numerical problem here? We saw earlier on that we have different scales for different variables. Like our medium income has a scale of like almost 0 to 15, but our population is in the thousands. To compensate for that, when linear regression learns these parameters, beta 1, beta 2, beta 3, the beta value for population would be huge compared to the beta value of medium income. As a result, what happens is it says that your model can fluctuate based on the value of your population. Hey, maybe why don't you bring all of your features into the same scale? So to bring values in the same scale, you essentially have to standardize them. What does standardization mean? Standardization means that you have to subtract the mean of your column and divide it by the standard deviation. This brings everything essentially, it centers your data at zero and it evens out the spread of your, this thing, your that particular column value. So rather than doing it manually, you can have a library do it for you. We can just use the standard scaler from scikit-learn. It essentially does the same thing, subtract the mean divided by the standard deviation. So we get this, we do this again. So you would have noticed earlier on I had just passed the x value here, this x value here. So what happened was when you pass this x value, because we had also added a constant term, it just subtracts the column of ones with one, which essentially gets it to zero. So we lose the interceptor if we just run standard scaler on x values. So rather than doing that, we have done it from scratch. We once again pass the data value without the dependent variable, and then we can just retrain it. We say, okay, this is our scale version, and please train the value on that. The thing to notice here is that your coefficient do not remain the same. So for example, the medium income, the coefficient is 0.7. Earlier, it used to be 0.37. Okay. These the thing is your coefficients, as I said, now because your data has now changed its scale, your coefficients will also change the scale. The result is essentially the same. Your linear regression is still pretty much the same, but the interpretation is slightly different because the range of your data values has now changed. Okay, so you could use either one, it's up to you. Linear regression doesn't actually care that much about the scale of your data. Okay, so if you would notice, we also have negative values in our population now because we have standardized it. So if we work with the original data and we just check, hey, so now that we have trained our linear regression model, let's check whether some of our assumptions hold. One of the assumptions is that your residuals should be randomly distributed along zero. That is, it should not matter what the predicted value or the dependent value is. The gap between the predicted value and the original value should more or less be the same for all of them. So when we plot it, we see that most of them do have this blob structure, that is they are randomly distributed, other than a weird straight line which is definitely not random, right? So what's happening here? So this is more or less you should know this by going through the metadata. Like whenever we get a data set, it is a good thing to actually go through the metadata first. So we notice that if you plot the histogram for the median house income, we see there is a weird pillar at 5, which is like very unexpected. If it looks like more or less a dying tail, that is as the number of As the medium income increases, the number of homes for that decreases, a tail heavy population. But there is a sudden sharp jump here. So this sharp jump essentially means a cap. What does that cap mean? So if we had not capped it, this would keep on going, like 5, 6, 7, 9, 10, 12, so on, so on. A very large value. For example, think about like these are your normal hotels in your area, but there can be some like luxury hotels which are very expensive. So that can go to a very large value. Like this is on a scale of, remember, this is 500,000. Value of 5 is 500,000. This can go into millions and billions, right? For example, for those luxury yachts, etc., etc. So they have just capped the value at 5. When you cap the value at 5 and you make some predictions based on your linear data, your residual essentially becomes something like this: my observed data minus my predicted data. The observed data, because it is capped at 5 for these particular values, it becomes 5 minus my predicted value. This is the equation of a straight line. Where your intercept is 5, you would notice this is essentially going in that direction. 4, 5. 5 would have been something here, and with a slope of -1, your predicted value. So that is the straight line that we are noticing here. So let us just remove these cap values, because they anyway should not contribute that much to our linear regression. It's a weird value to have. So we just drop it. We can say, hey, I don't actually want these values that are greater than 5. Let me just drop it. So our uncapped value looks like this, and we again fit a linear regression model on that. So we get more or less the same thing. We have a positive slope with medium income, and the rest of them are also doing good. Okay. And when we again plot a residual model, we get, for example, this thing, a blob at the zero values. And once again, to check the heteroscedasticity, that is, does the, variance increase or decrease with our x values, we can use the QQ plot once again to do this. In fact, the QQ plot would also change depending on whether we used our, did we compute the residuals? Yeah, we computed residuals again. We could also do residuals uncapped in a separate plot. You see, this changes. In this case, when it reached 5, it goes above the 45-degree line. In this case, it stays below the 45-degree line, depending on that. So you can again make a case for either of them. So this essentially concludes your multiple linear regression pipeline. It is more or less the same for all of them. You start out with the data, you look for correlations, you remove multicollinearity, you train your model. If you see any sensitivity, you should, in fact, in general, standardize your model upfront, check for the residuals, whether everything is okay, whether the assumptions hold. And if you see any weird stuff, you can go back to the data and clarify whether there was any like a cap value or something. And finally, you have these plots to conclude. So that's it for today. If anyone is new here, let me clarify that we always upload the code for our sessions at this GitHub repo, and the same thing can be found on this YouTube playlist as well, the recordings of the same. Okay, so let me paste the two here for you. We have this, we have this, and with that, we can close. See you all next week.